draft physics video presentation. DraftScience here on YouTube. Alright, some more double slit stuff, just to re-emphasize the point. It connects to everything, really. I mean, scatter of small particles in the atmosphere. It sort of explains why the sky is blue and why the sunset gets red, and their explanations are kind of bogus. Their understanding of everything. I mean, in this video he's explaining why AM radio survives mountains better, and it's a silly explanation. So they really just don't have any of this right, and they've been teaching it for hundreds of years now, since the Young experiment, and when they decided everything's a wave. And it's just all wrong, and it doesn't really work mathematically, and they just kind of do a generalization and pretend, oh yeah, no, if you really do it, it works out. But it's just junk as physics. And you would think somebody would have been, of all the physicists in the last 100 years, you think there'd be a few of them who decided to specialize in this one kind of subject of photons and how they behave. And you think they would have discovered that what they're saying just doesn't make any sense, and that they need to start over and come up with a better theory, because this one doesn't work. And it's just it's a pretty glaring indictment of the fact that there just isn't enough oversight. There's no devil's advocate element. There's no that'd be a good example, except we don't have to call it the devil's advocate. We could just say there's the, don't jump the shark, don't embarrass yourself, don't do something too fucking stupid advocate. Some lawyer who just shows up, a third lawyer at the trial, who just kind of said, hey, that guy's cheating over there, he's sort of pulled something. Oh yeah, they're talking shit. Just somebody to put it in a little bit of context and say, you can't buy that argument. Here's some flaws in it. I'll help you understand why what they're saying is nonsense. And there just isn't any of that. It's like the Feynman video. I mean, I played it and I'm showing you how he's saying things that are just silly. It's not the truth, and it didn't happen. And that's important context, because you'll be very confused if you don't know that they really don't have any evidence for this stuff. You go back to even the Eddington experiment, the whole, light is bent by gravity, and here you have kind of a bold claim that one single thing going the speed of light is affected by another force, another thing going the speed of light. And it happens nowhere else. In all the experiments we can do, we can never make a force mess up a force. We can never hit a laser beam with a laser beam kind of idea, or any other kind of beam. We always need matter to be a catalyst to any interaction between forces. There always has to be a monkey in the middle, or there's no game for the forces to play. And that's the truth. And so here you have this bold claim, not only that one of the forces is bent by gravity, but that it's bent twice as much as everything else. But not magnetism, not electricity. No, just this one little special thing is affected. I always want to pause when I say the word electricity, because there really is no such electric force. It's really just magnetism. That's the only thing you can turn on and off, and that's the only thing you can play with, really. It's always about charge in the end, so I guess I should say that to be more clear. Well, anyway, it's just kind of a mushy ground, this idea of more than one polarized force. The two of them blend into each other too much to be able to make these distinctions, I think. But anyway, so this is a video by some Robert Ross. He's apparently a teacher of some kind. But there's just no information on the channel. He's blocked comments. I imagine he was doing it as some supplement for his students. I don't know why he didn't just make them unlisted videos then. I don't know. But anyway, it's just really bad anyway. So I just thought, okay, let's play it. Um, because it's just really bad physics. But there's no way to contact this guy, so I can't really tell him ahead of time, hey, you're doing really bad physics and you got these videos public on the internet, and they're really bad.
Okay, that was Max giving you a good morning welcome.
Whoa.
All right. So, do you remember last session?
All right, we
said
we
that
definitely need more volume. Oh no, it's my fault.
go on to electricity. All right. So let's just recap what we learned last time. At the
No,
end
it's
of
still
last
not
session,
good enough.
we came up with an approximation formula of x over L equals lambda over d. Okay. Well, what does that mean?
Pause.
It means that when you have two slits and you have a screen, that the
Pause.
distance between here and here,
Shit.
between slits
Alright.
and screen is.
Yeah, all right. We should be all right now, I think.
Remember last session we said that this is going to be our last day teaching waves. Well, I was wrong. I think today is going to be the last day teaching waves before we go on to electricity. All right, so let's just recap what we learned last time. At the end of last session, we came up with an approximation formula of x over L equals lambda over d. Okay, well, what does that mean?
Right. Well, you really don't need to do this stuff, right? I mean, all you're really saying is that all that's going to matter to reconstructing photons is getting them back in phase. So it's just a wavelength of difference. So you're just talking about putting things back in phase, and there's a certain number of places you can do that. You'll always be able to calculate it that way. There's no infinite planes. There's no infinite amount of diffraction. There's none of this nonsense. There's sources that are causing the effect, and that's been clearly pointed out that it's obvious that the sources are the surfaces. And it just doesn't make sense to create a little tiny Huygens wave right on the surface, because it has to be right on the surface, because the surface is, in fact, sending photons in both directions in what appears to be an equal amount. And so there's just no way of getting around it. You have to put a little tiny wave right on the surface. Not in the middle, nothing, no rational place for a wave to be. In any other wave circumstance, the wave wouldn't be created there. And that's where all of the fringe pattern is being created by. Not just part of it. I mean, all of it's coming from those surfaces. All of it. Everything goes through the middle, just goes straight through. It's unaffected. The only way you get a fringe pattern is because right on the surface creates it. That's what's been demonstrated to you thoroughly, clearly in my previous video on the subject. I'll leave a link in the description. Goes through the whole thing. It's over for wave theory.
It means that when you have two slits and you have a screen, and the distance between here and here, between slits and screen is L, and the distance between the two slits is D. Okay, when light comes in, which has some wavelength, light comes into this two slits with some wavelength. Okay, we ended up getting some.
Right, so he uses this ambiguous D. He doesn't draw it explicitly. Do you mean this distance? Do you mean the center of the slits? Do you mean the edge of the slits? Nothing. So obviously, if he did this sloppiness, okay, there wouldn't be any equation, right? The distance is always when they use one distance in the double slit experiment, that is when they do the experiment so poorly, they're not even counting what the other two openings are doing. They're basically treating it as if it was a single impediment. That's all they're doing. They're just saying it's not the double slit experiment, it's the single needle experiment. And you won't get the right answer if these slits have any kind of opening. So if they're more than a wavelength in size, okay, that is more than some preposterously, sillily narrow slit, you're going to get huge consequences caused by that slit opening, the distance from that other surface. It's going to completely change the pattern is the point. So this math doesn't work. Okay, it doesn't work in 99.99% of the possible two slit experiments you could draw. This math won't work. It won't get you anywhere close to a right answer. Not even close. It's going to miss all the little bars altogether. They don't exist. It's only detecting one pattern, that is the envelope. And it's ignoring all of those little, all the dots that make up the pattern. So it can't help but fail dismally. So I'm just pointing out, it's just so inexact. It obviously doesn't acknowledge the truth, which is the Young drawing doesn't work, and wave theory doesn't work in the sense you have to understand this experiment as 4-point sources. That's what works. Clearly. I mean, and it's just not that difficult to know it. So why has physics for all this time, not one single physicist could stand up and say, this analysis is rubbish, it's just garbage. It doesn't work. Why are we using it when it doesn't work?
A interference pattern on the screen. An interference pattern on the screen looks something like this. You got a nice bright line here, 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 here. So you've got bright to dark, sorry, bright, dark, bright, dark, bright, dark, bright, dark, bright, okay, and so on. And the video link that I sent, okay, there's a video link on YouTube of this actual experiment being done, and it's really actually a very good video. And you'll see
So again, another citation to the rubbish videos by Veritasium. Okay, so it's just sad, but yeah, this is the definition, right? They just go to some other guy who did it wrong, and immortalize that piece of garbage, that bad analysis.
There's a red laser, and you ended up getting all of these this interference pattern.
Yes, anyone watching this video should be familiar. There's two, distinctly different patterns: single slit, double slit. So yeah, if you have to explain all that stuff, you probably shouldn't be watching this video.
Goes on to explain also that the brightest line occurs here, right at the center. So the brightest line is here, and then it gets.
So in the double slit experiment, it really isn't all that much brighter. So that's the huge difference, and that's largely because the whole middle of the beam of the laser is getting blocked. So obviously you don't have nearly as strong a light going straight through the slit.
Not as bright over here, and not as bright as you go further away. So,
yeah, for different reasons, right? The first reason is the two little slits are really close together, so they just send the light through. So there is light going straight through the two open slits, so the center is going to be brighter. That's one reason. And the other stuff's going to be duller as it goes further away, because the odds of a photon or a piece of a photon getting scattered at the extreme angles is less than the odds of it getting scattered at the stronger angles. More gets deflected a little bit than gets deflected a lot, which is just basically pointing out that you're more likely to be there's only a certain number of photons that go right exactly next to the surface, and as you go further away, there's less and less potential to interact with an electron and to be scattered.
So the intensity graph would look probably something like this.
So it doesn't look something like that. The double slit creates, obviously, the envelope pattern has two patterns. It's just not much point in drawing it in this way, but anyway, it's just wrong. But go ahead, whatever.
Very intensive. Most intense here, in the intensity in terms of brightness. It's brighter here, and it gets less bright as you go further from the central maximum.
Right, and it starts to get brighter again, and then it gets duller, and then it gets brighter again, and it gets duller. Yes.
Okay. But at the central max, okay, last time we also learned that since the distance from slit 1, this is slit 1 over here, this is slit 2, that the distance from slit 1 to here and slit 2 to here, same length.
Yes, and as I pointed out, that's a fake notion of what's really happening in terms of the wavelength differences. So if you want to measure the real wavelength differences, right, let's use Mr. Arrow. I guess he's a Mr. I don't know. So the idea would be is from these 2 points you'd have equidistance, and that's true, and you will get, but you have to understand those 2 points are less than a millimeter apart, and you're projecting the image meters away. Okay, so it's still only a millimeter apart. It's still inside of 1 millimeter. The fact that those two lines are the same length only happens inside of 1 millimeter. So a pattern that's inches across, a foot maybe, okay, 1 millimeter in the middle, there is a bright, okay. but it doesn't have anything to do with what the real distance is from the actual sources, in a sense that if you want to get their accurate, if you want to understand what their wavelength phase is going to be, you have to draw the lines going to the 90-degree point. So you draw two equidistant, a line from this slit, that edge, this edge, and you see that difference in those lines, and then you arc around this way. And that'll tell you what this midpoint is. So when you do the math and you divide, you can just divide the wavelength of the light into the distance of the opening, or the distance between the surfaces, and that'll tell you how many wavelengths fit in there. And if it actually fits with an unround number, that is, if it goes in some odd number of times, or it goes in with a remainder, then you're going to be pretty much assured that this middle point actually will be some kind of darkness, not a full bright, when it's actually going to be displaying the pattern that matters. The pattern, the fringe pattern, the scatter pattern. So anyway, when you actually do it, you'll find that's the truth. So this is just a fake, because it's happening inside of 1 millimeter. The real scatter is going the out direction. The fringes are being created out here and out here. They're not being created inside 1 millimeter of distance. That's not where the fringes are. And the fringes are being dictated by a different rule. It's probably good enough way to say it.
But since they were the same length, they were off by 0 degrees or 0 wavelengths. Okay.
Right. So I'm just saying the easiest way to understand that is that stuff happening inside of 1 millimeter isn't really part of the fringe pattern. The fringe pattern is all being created by the scatter, the light near the surfaces. It's all dictated by these distances between the surfaces, and they're dictating whether the light can possibly be in phase or out of phase. So there has to be essentially 4 photons in the experiment. Okay, there has to be a photon interacting with each one of these surfaces, and what you're basically going to do is just send pieces from each place and reconstruct photons.
Okay. And that's why you got a bright line. Okay, it's constructed experience. All right, so let's just do some of the mathematics. So let's do an example. Okay, so we're using the formula x over L equals lambda over d, and again, that's an approximation formula, and we showed how for small angles, since the tangent of theta and the sine of theta were equal, approximately, we were able to use this, and we talked about that last session. Okay, so the question is, well, what would happen if, let's say, here's your setup, okay? Let's say you were to take the L, okay, the question says as L, actually, you know what, we're going to first manipulate the variables. Okay, so here's...
I don't know if this is very useful, because this really isn't an equivalency. They're just playing the game, blah, 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 blah. And the only thing that really matters, okay, isn't dividing the distance into the wavelength. Again, it's just backwards. Divide the wavelength into the distance, and it'll just tell you exactly how many wavelengths fit in the distance. It'll tell you how many nodes, how many fringes you're going to get as a total number in this 180-degree arc. It'll tell you exactly how many possible locations there are for there to be a wavelength of difference in the distance. And again, this idea that you can do the middle of the slit is in the math. It never is in the math. So, it's just, this is so fudgy to stick these arrows in here. The light that goes through the middle is not being affected. It's just nonsense to think so. The only light that matters is the light on the surfaces. The surfaces is where the lines have to be drawn from. That's when the vectors are from. And those are entirely dictating the fringe pattern. So it's clearly just scatter completely explains it. It explains why there's a pattern. It explains the whole thing. It fixes all of the weirdness, and you don't need to believe in any of this extraordinary claims. You don't have to believe the extraordinary claim that a photon is interfering with a photon, that a force is interacting with a force, because it's not, because they don't, because it doesn't happen. So there's just no reason to believe it, because it just doesn't happen anywhere else. Gravity doesn't affect gravity. Gravity has to get to a material body to affect something, to make something happen. It can't bounce off of gravity. Oh, damn.
X on your screen. Okay, X would therefore equal, if you cross multiply, you end up getting lambda L over D. Now, if you notice, X and lambda are proportional. X is proportional to lambda. X is also proportional to L. But D, they are inversely related. So X is inversely related to D. Okay. So to answer the question, as L decreases, X decreases. As D decreases,
This is just because you're projecting it on a screen. The pattern's getting bigger. Of course, it's proportional. So this really doesn't mean anything.
X increases. And as lambda decreases, X decreases. So when we say that X decreases, instead of seeing, let's say, here, I'll just write this up over here. When X decreases, a decreasing X pattern means that instead of...
So again, just to simplify, the math is so simple. You just do the wavelength, okay, lambda, into the distance, d. If your number, you know the center is basically going to be half that number, okay? That's the truth of it. The center point will be half of that number. And so if you have a remainder, if you have like 15.7, right, and then you do half of 15.7, you get 7.577 or something. You know that's not around a whole number of wavelengths, and so you know the center is technically going to be an off, the real node. But anyway, continuing.
Seeing something like this, where that's X, a decreasing X pattern would mean that you see something like this. Okay?
Right, so he's just pointing out that this is just wavelength differences, right? So how much the light is scattered is dependent on its frequency. And really that's just about its polarization. In the end, the polarization is proportional to frequency, and that's what's sort of determining. But obviously there's more wavelengths. So if you use blue light, obviously more wavelengths into the same distance gives you more nodes. But the reason why it gives you more nodes is because the higher frequency light has a smaller polarization.
Where this distance is UX. Okay? All right, so let's do the example. The example says, what is the wavelength of monochromatic light source when it passes through a double slit with a separation of 3 times 10 to the negative 4th meters? The screen is 4.35 meters from the slit, and the first bright line appears 0.01 meters from the central maximum. Okay, well, the first thing we're going to do is identify which variables are which. Okay?
So I guess we won't bother with this. We've seen this 4 million times. And again, it's the simplification is based on, again, there's no, in that equation, in this math, the slits don't exist. It's not in the equation, okay? He's putting the distance of the impediment in the experiment. There's nothing else in it. So he hasn't even accounted for the 2 extra surfaces, so he's just going to get the wrong answer, which is the envelope pattern.
All right, what type of light is that? Okay, well, you need to go to the reference table and see, is that visible or is it not visible? Okay, if you go to the reference table, you will see, hopefully, that the color is blank. Okay, go to the reference table, check it out, pause the video. Great, all right, you're back. Turns out that the frequency is in the red frequency range. Frequency range of red on the physics reference table is between 3.84 times 10 to the 14th hertz through 4.82 times 10 to the 14th hertz. Okay? All right, so that was that problem.
So they never do these problems by actually having, measured a slit ahead of time and then measured the bars on the screen and then ask the question and see if you get the right answer, because they're just saying they got the right answer. There's no right answer here. You won't get it under these circumstances because it's not the double slit pattern in the first place.
Okay, example 2. Example 2, once again, we're going to use the same approximation formula. Okay, and it says x over L is lambda over D. Okay, if x is 0.01, And
So, so again, they're just taking one distance, and that's all we're going to get.
L is 2 meters, and the distance, and lambda is 5 times 10 to the minus 7 meters. All you do is you plug it in.
Right. All you do is plug that in, and you're missing the slit width. Okay, so it's not in there, and so all you're going to get is the envelope pattern, and it's not going to tell you anything about really the experiment at all, because you don't have the dimensions that you need to be able to dissect anything. It's just nonsense. So this is just a nonsense problem from a non-existent pattern where they just made up a pattern and made up a location.
Plus multiplied. And D comes out to 1 times 10 to the minus 4 meters. Okay. Now, since the setup looks like this, okay, that's L, this distance here is D, and X is somewhere over here. First question says, or question B says, at point P.
So again, this ambiguously drawn D. Woo, yeah, we just make up. So it's a middle, it's this slit, it's this surface. Who knows where the D is? No.
P, that's point P.
The D has to mean something. And what it means when they cheat this math is that the slits are so small you wouldn't even be able to shove light through them barely. It's just a fact. They're so small they would break the light, all the light going through as actually broken. No photon could successfully navigate the slit. It's so small. That's the funny part. The polarization of all the photons makes it impossible for you to jam through any photons, essentially.
It says, what is the path difference? Okay, and we already talked about how the light goes from here to here, and it goes from here to here.
Okay, so he draws his little squiggly, wavy bullshit, doesn't make any sense. And again, it doesn't do it from the middle, so he drew it from the middle of the opening. Nope, none of the photons are going through the middle or going anywhere, okay? Only the ones from the surface. Those are the only lines that make the math work, and you have to do it from all 4 sources. So again, it's just nonsense, garbage, rubbish, gibberish. It's so bad. It's so wrong. And it just shouldn't be just me saying so. There should be some concession by people who can have reasoning skills and can understand that, yes, Gary, you're right. The real distance, no, I might as well draw it just to point it out. It's in the other video, so I probably shouldn't, but yeah, we'll do it anyway. Just to remake the point. Alright. Yeah, that's good enough. Somewhere on the board? Yes, it is somewhere on the board. Okay. So, slits. So if you do the single slit, this is the only distance that matters, obviously. Okay, right there. Or the single impediment, right? If I just made a single impediment, you'd understand that, the same distance, right? It'd be the same exact math for a single impediment or a single slit. And really, all the math is telling you is there's basically, I could take a point here at 90 degrees, and I would know that one's telling me exactly, okay, the line difference. What is wrong with this piece of chalk? It's very nice, this little chalk holder, but this chalk has a fillium on it of some kind and it won't draw. Yeah, sorry. Technical difficulties. Alright, so at 90 degrees, you'll get the full distance difference. So these 2 lines from the 2 surfaces will have a distinct difference, and that difference will be exactly represented by the number of wavelengths in here. So you can basically just say, I could just put those notches, right, this extra line notches, I could just put them right here on this, right, and that'll tell me exactly where the wavelengths are, and I could just swing that on an arc, and that'll tell me, okay, oh, this point I hit a notch, 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 I hit a notch. And obviously when I get to the middle, right, if this comes out an odd number, let's say I had 17, okay, well, whatever the number is. I'm just saying you can understand that I could end up with 8.6 here, dead in the middle. And then obviously that 0.6 is saying, oh, that's some portion of a wavelength. So I haven't started a node yet. So I'm really going to always end up with node here and node here. And the laser is going to fill in this part in the single slit. And that's why I always have this double node in the middle. Is because it's really very unusual to be exactly a whole wavelength of difference, right? That's really hard to do. And even if you did it, you're having it here. So you're already breaking it again. So you have to have a very special, a slit just at a perfect distance to fix this problem, because this is where the pattern really starts, are these two lines, and this 0 point isn't a real point from the line perspective. The lines are you're always comparing two vectors going the same direction. In this one circumstance, you're comparing two vectors going in opposite directions, and so that's sort of the giveaway that tells you this is very different than what's creating all the fringes. The fringes are being created by lines going in the same direction. So that kind of gives you an understanding of why you can't be fooled by this thing in the center, because that's just a tiny thing happening inside of one little tiny, less than a millimeter, 0.5 of a millimeter. That's happening. These two lines are the same length. But everywhere else, these lines are not the same length. From here to here, they're not the same length, and from here to here, they're not the same length. And that's where the pattern really is. So anyway, they're not a wavelength of difference in their distance. But anyway, so with this simple formula, you can understand exactly how many nodes you're going to have ahead of time. You can know you're just putting it on a pi radius, so you can just do I'll just multiply that by pi. And that'll tell me exactly how long this line is, and it'll tell me exactly how big the nodes are. And I don't have to do any sine theta. I don't have to do any small angle approximations. I don't have to do any of that crap, any of that nonsense, any of that rubbish. All right, two slit very quickly. So obviously, when you have two slits, all right, there's two distances. There's this furthest distance, okay, between two surfaces. So I could draw those two, the line differences. I mean, the difference between this line and this line. Oh, huge difference. Huge number of wavelengths in there, right? And that's what's causing the little pattern, right? The little bars. And then the big bars are being created by this, which has a much smaller distance difference. So that's the big envelope pattern. Okay. And and where those two overlap is where you have a pattern. So you'll have bars here, and then you'll have bars here, and then you'll have bars here, that kind of thing. And there's really two distances that matter. And that's the math that actually gets the right answer. And it doesn't matter how big I make the slits. I can change this distance, I can change this distance, I can fiddle with it any way I want, and that math always works. And the secret to it is the fact that there are 4-point sources. All right. And so what happens is as you add the second slit, you have 4 times more photons made, okay, because you're adding a capacity to multiply the possible permutations. So it's like the odds of rolling 7 when, a dice that add 2 dice that add up to 7, when you have 4 dice versus 2 dice. It multiplies your odds, something like that. It's probably a better example, but the point is you're sending the more parts, the more capacity to utilize the ones you've already sent. And so the trick is that with just one slit open, you get 1x light. Okay, with this slit open, you only get 1x. But with both slits open, you get 4 times the intensity, because you've added these extra parts that multiply the capacity. You're not only adding the photons that are in phase from here, you're adding the ones you combine this line with this line and this line with this line. So you're multiplying more potential additions. So that's what's fooled people, is this 4 times thing. Because then they say, well, this one got darker. No, it didn't get darker. The one next to it got much lighter. Okay, so that's what really happened. There's a little 1x here, okay, that seems to be in the wrong place from one slit open. But that little 1x is outdone by the 4x difference. So the 4x pattern overwhelms any of the individual patterns created by either slit. So anyway, yeah, that should be enough to, yeah, I mean, that's the simple mechanics. It screams the point sources win. The real math that works is the point sources, is the surfaces. There's no denying it. That's the real math. That's the one. That's the math that actually works. And there's no denying that there's no good reason for there to be a wave here. Okay, here, 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 and here. Okay, I mean those are silly places for the waves to be. So, wave theory is dead. It doesn't work. It doesn't explain the pattern. It fails. Yeah, there's nothing else. Is there a reasonable alternative theory about how the wave theory doesn't fail the test? It fails the test. The scatter succeeds in explaining the phenomenon. Waves fail to explain the phenomenon. Is there some other reasonable way to interpret the facts? No, there just isn't. And if you keep insisting, then I'm just going to say you have to be an unreasonable jerk. There's no other explanation. If you keep insisting, against the evidence, bad on you.
And the difference between these is simply one wavelength. Okay, so the answer is 1 wavelength. Okay, so the answer to part B, 1 wavelength.
Right, so they just keep doing this complicated thing of creating this extra triangle to figure out there's an extra amount of distance when you already know there's going to be an extra amount of distance here and here and here, and you keep moving it over. And again, projecting on a flat plane completely breaks the math because, see, he's using the same L, right? Now, when he's going to do his math, his L is going to go in this new direction, right? Now, I don't know if the mouse is visible, so I guess I'll use my arrow. So L is here, right? From here to here, a straight line. Obviously, L going way over here is going to be a much larger L. So they've really predicted where the pattern will be on that arc. They've predicted the space in here. They've predicted what it would be if it landed there. They didn't predict what it's going to be when it lands over here, further away. So it's kind of very deceptive that they don't even get their math correct in the sense of understanding that L distance is much larger. And it's going to distort your pattern. Can't even get that right.
What about C? It says at the second maximum. Well, the second maximum, they're off by 2 wavelengths. That's right. And at the central max, you mentioned that they are not off by any wavelengths. So 0 wavelengths apart. Okay?
So again, at the center, they will be wavelengths apart. The fringe pattern will, in all likelihood, not be dead center. I mean, there won't be a bright in the very center. I mean, from the fringe perspective.
That difference. All right. Last thing. Okay. See where it says important question? Okay. So the important question is, let's say you're driving through the mountains. You're driving through the Catskills.
I have a headache.
Okay? And I don't know if you ever notice it, but sometimes if you have your radio on FM or on AM, there's the mountains, sometimes your radio stations give you a bad signal.
So this is just really bad. So this gets sort of to the scatter argument, okay? In particle scatter, and so why the atmosphere is blue is because the small polarization of the blue light means that it can hit a small particle, all of it, and reflect, generally speaking, in the same direction. And so we're likely to see it. Where if a red photon, a big photon, hits a little particle, it just knocks one little piece of the red photon off. It's more likely to just break a piece off. It's not as likely to be reconstructible. Now the trick is, though, in the forward direction, if you're looking at the sun set, now it's all red because the blue light's all broken. And the point would be is that, yes, of course, the blue light is got a small polarization. When you're scattering the pieces off, it's less likely. You have to bring it back to a small polarization. You have to take the pieces and put them back in a small box, and you're less likely to do that. But the red light, you've scattered a bunch of pieces, and now you're more likely to be able to put it back together because the red lock, the box that the red photons have to fit in, the bits of the red photons, is much bigger. So you're allowed, you have more flexibility because you can have more expansion. So everything you're seeing, pretty much from a sunset, are photons that are being remade. You basically blocked all the functional straight line photons, and now we're just getting a bunch of ones that have been remade out of slightly bent ones, slightly deflected ones. And that's why the image gets bigger and all blurry. But anyway, there's no diffraction. This has nothing to do with diffraction. It has to do with scattering little particles, and it has to do with how much they're scattered based on proximity to a surface. Obviously, it's like our shadow. Our shadow only fuzzes the very edges of the distant shadow. You can see it get fuzzy. And so it's not much scatter going on, right? The fringes are very narrow in how much they're scattered. When you do the two slit experiment, you're emphasizing, you're exaggerating the effects to make them more visible. You're magnifying them and all that kind of stuff. The real effects are kind of very small and slight. There's only a slight amount of bending.
Okay, and the question is, why is that?
And bending is the wrong word to use, probably. It's only a slight amount of scatter.
The important question is, if you're traveling through the mountains, should you be on AM radio or FM radio? Now, AM radio is generally of the frequency of kilohertz. Okay? FM radio is on the order of usually megahertz.
So you could describe this as that FM's blue light and AM is red light. That might be one way of just making a quick analogy, just simply pointing out, obviously the FM frequency is very small, measured in centimeters perhaps, a feet at the most, and then AM would be measured in meters, that kind of thing.
Okay, so of these two, which one has a higher frequency? Well, kilo versus mega. Okay, I'd rather have megabucks than kilobucks. Frequency of FM is greater. All right, so FM has a higher frequency, high frequency. Okay, but if it has a high frequency and V equals F lambda, the higher the frequency, the smaller the wavelength. Those are inversely related. So this has a small wavelength, which means that AM has a longer wavelength.
So again, this wavelength thing, we're talking about the distance between events, really. So we're just talking about the period. It has a longer period of time. You can shoot a gun once a second or once a minute.
All right. So here's the Empire State Building. Okay. And
bad example really, because most radio doesn't come from there anymore.
Say it's broadcasting Z100. Okay, and that's a FM radio station. Okay, so you're driving through the mountains. Okay, and the question is, when you are, let's say, on this side of the mountain, what are you more likely to hear? Okay, well, let's think about this. So the signal comes in. Okay, with a high frequency. Hits the mountain. Actually, let's draw this a little bit better.
You should have a better theory. Your drawing is the least of your problems.
Signal comes in, high frequency, it hits the mountain. Well, what does it do when it hits a mountain? Well, generally the ray comes in, and it's going to reflect. Okay, but what else happens? What happens? What's the definition for when a wave hits a barrier or obstacle? That's right, diffraction. So some of the wave is going to diffract. Okay.
So this is just nonsense. There's no theory that FM diffracts more. That's just nonsense. The photons, the red, blue, or green photons that you're going to shoot through a slit experiment, for example, they're all scattering to all locations equally. There's no difference between how much they're scattered. So the pool of light, if you send white light in, a bunch of white pieces go to all the locations. The point is only in certain locations, again, are you going to be able to have a wavelength of difference. So you're only going to see blue light reconstructed here. You won't see the blue light that's right next to it because that's out of phase. And then you'll see blue light here again. And the red light's, again, based on its wavelength. But there's the same amount of stuff going to all the places. It's just about what pieces you can put together, and the ones you're going to see are the ones that are going to be back in phase. And that's it. So, but there isn't more or less scatter. So this is completely a wrong theory as to why you could hear an AM station and why you wouldn't hear an FM station. The real reason, again, is back to polarization. The fact is the AM has a much wider band, less of it gets wiped out by the mountain, and therefore more of it survives the process of hitting the mountain. Where the FM with the narrow band, much more of it gets wiped out by any interaction with the mountain. And again, it's back to that argument of cramming something this size into back into the small container. And so you can't put the pieces back together as easily, and the AM is much easier to put back together.
But turns out that, I don't know if you noticed it, if you've ever gone through the situation, but the FM radio stations really cut out. Okay, it's really hard to hear FM radio stations when you're going through the mountains. You'll hear it clearly, and then it won't hear it clearly. But the AM radio station that's broadcasted, well, it has a smaller frequency. Okay, the wavelength.
Yeah, well, part of the opposite is true if it's cloudy, because then the FM will bounce off the clouds better than the AM, and so you'll be able to get your radio from the sky.
Are longer. So when you have these smaller frequency, longer wavelengths, okay, yeah, they're also going to bounce off the mountain, but you hear them better because they diffract better.
Okay, so they don't diffract better. There's no there's no photon gives a crap, right? The photons don't care. The photons are indistinguishable. The constituent parts are all the same. The same parts making the red light are the same bits that make the blue light. They can't react any different from each other. So it's just nonsense to think one bends more. No, the point is you can reconstruct it at longer distances from each other. And that's it. Further from each other or closer to each other, depending on a wavelength. So he's taken something you see in the two-slit pattern in the sense that the blue light is narrower. There's more bars of blue than there are bars of red, obviously. When you do that wavelength into the distance, you'll get more blues will fit, more blue wavelength will fit into the distance than red wavelength, obviously. So obviously the blue nodes are going to be closer to each other because there's more of them. It doesn't mean that the blue didn't get bent as much and the red got bent more. So anyway, this is so bad.
So the answer to the question is, why do you hear AM radio stations better in the mountains than you hear FM? And that's based on the amount of diffraction. Okay, so
no, it isn't. They both get diffracted the same amount. The point is the AM is easier to reconstruct. It's that simple.
Answer is hence blank wavelengths diffract more. Well, what's the answer? Hence longer wavelengths diffract. Okay.
All right, well, it's just wrong. Okay, it's a statement. He has no proof of that, no evidence of that, nothing. It doesn't diffract more. All right. Just doesn't. There just happens to be more wavelength differences. When you have a smaller wavelength, there's obviously more wavelength differences. More locations where you can reconstruct the photon. But they're going to be smaller. There's more of them, but they're going to be smaller little bars.
Okay. So now the question is, well, now that we understand that different frequencies diffract different amounts, let's predict which bends more.
Okay, so he's saying it. It's just so wrong. Sorry, just really wrong, really bad. Through
the double slit. So X over L is lambda over D. Okay. So let's say we have a double slit pattern. Here's the Young's double slit experiment set up. And
right, so the blue light, the red light, all spread exactly the same amount across that surface. And all you're doing is you put blue light together in smaller packages, smaller spaces, and more of them, and red light gets reconstructed in fewer spaces, but the bars are bigger. That's all. That's all there is. Same amount of photon bent. So if you were to measure the actual amount of photon you were receiving in any one area of both blue and red, it would always equal the same amount of photon.
We end up with, let's say, red light. Okay, I'll use orange. Okay, I don't have red. Okay. Let's say here's red, and here's the pattern. Red, 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 red.
Right, so you should draw them bigger. Okay, reds are bigger. Okay, they're not just further away, they're bigger.
Okay, so I shine in red light. The question is, what is going to happen if I were to switch the laser to green? Well, let's go back and talk about Roy-G-Biv. Okay. Of these colors, which one has the...
I guess that's red, orange, yellow, green, blue, IV.
longer wavelength?
Indigo, violet.
As you recall, as you go towards violet, you have a higher frequency. Okay? If you have a higher frequency, you have a lower wavelength. Okay? So of these two, red versus green, which one has a longer wavelength? Red has a longer wavelength. Okay? Well, if you have a longer wavelength, if the wavelength is longer, and wavelength is proportional to x, the longer the wavelength, the bigger the x. So if we were to...
And also, the bigger amount of space it's going to occupy.
Switch this with green now. What should happen? We switch this with green laser light. Well, since green has a shorter wavelength, smaller wavelength means that the x distance is smaller. So the pattern for green would look something like this. Green, 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 green.
Better to do it with blue just to emphasize the point, because then they come up actually on the third node. They're almost in the same location, because the blue is almost half of what the red is doing, almost. But anyway, yeah, nothing more to say about this, I suppose. There's probably some differential about what percentage of the light does survive the process in terms of proximity, size, polarization. So there might be some slight differences in the volume of light. So I shouldn't say exactly the same amount, because just like with the scatter argument, small particles will damage one form of light more than they damage another form. And likewise, big particles will affect one form more than they affect the other form. So, anyway, enough of the video. Just too terrible.
Okay, so the x distance would decrease. All right, that is it for today. And actually, we are done with waves. Yay! So the next...
Okay, so can't tell who this guy is, but anyway, who's he's teaching, you know. So very bad, horrible, horrible way to explain it. Just bad science, bad theory. I don't know. I just don't. I don't know why somebody didn't fix this. It just seems so funny that I had to show up to do it. Quite strange. Anyway, so till the next time and such, when I will continue not to get any reasonable counter arguments. Yay. Yeah, because the world is just full of assholes. Belligerently asshole-ish assholes. I mean, they just won't, you'll never give up on being an asshole, right? You're just going to cling to your religions, your God theories, your mush, your silly notions. You just will not have. Nobody can talk bad about my heroes, and your heroes are not very heroic. Not my fault. You didn't pick better heroes. Till the next time and such.